Great, welcome back everybody. I hope you've had a good afternoon at the workshop. This morning we were speaking about computer science as a discipline, or computing as a discipline, and if anybody epitomizes computing as a discipline, it would be Professor Sir Tony Hoare. So welcome, Tony. It's a great pleasure to have you here. Tony is one of my colleagues at Microsoft Research, so I have the pleasure of seeing him most days. Just along and around the corner, but not all of you have that pleasure, so it's great that you could come and be with us today.
Thank you very much.
Do you know, this is, Tony's been with computer science a long time. You're teaching our students the quicksort algorithm. Well, Tony invented that. If you ever teach them Hoare logic, well, unsurprisingly, Tony Hoare invented that too. And I think your talk today is a bit about computing as a discipline, stretching back rather a long way, not something newfangled, but something quite ancient. So thank you, Tony, very much for coming. It's over to you.
Well, thank you very much, Simon. That's a splendid introduction, but even more, I should like to thank you for your introductory talk this morning, where you gave me the idea, which I shall be now talking about. The idea is, as you may recall, that we should concentrate our teaching on what is permanent and changes slowly in our discipline, and balance the practical work of computer science and the applications of computer science with a deep understanding of the principles. That's one of the problems. Thank you. A deep understanding of the abiding principles, the principles that remain true more or less constantly throughout time and are not subject to the vagaries of fashion. Now, the point is, how do we recognize the principles and the permanent understanding from what is merely ephemeral or fashionable? And the answer is, principles that have been understood many years ago and which have been taught over many years to many generations of students are likely to be a little bit more permanent, a little bit more stable than those which arose yesterday or the day before. So that's the message. What I would like to do, Simon, with your permission, is to change the title of my lecture from Applied Logic to Great Ideas in Computing Science, from Aristotle to Euclid. Of course, I've told you what I'm going to talk about. The father of logic, deductive logic, is Aristotle, who lived in Athens in the 4th century BC. He was also well known for being the founder, or rather the father, of biology, particularly classificatory biology, which placed all the animals of the world into categories according to a family tree with genera and species and subspecies and families. But it's his logic that I will concentrate on and just describe his biology as an application of his logic, because I think probably his biological classifications influenced his style of logic. So, Aristotle defined what, as far as I know, is the first logic by first of all defining the language in which the judgments of that logic would be expressed. He noted that in ordinary language, a sentence could be composed of two parts, a subject and a predicate, and he said, let S stand for the subject of a sentence and let P stand for the predicate, and he allowed 4 different forms of sentence, one of which began with all SRP, no SRP, some SRP, and some S are not P. Those are the 4 judgments that he made and dealt with, and in later times they were given names A, E, I, and O, which we will see again. This is rather interesting that Aristotle knew about symbolic grammar, because we still define our programming languages in a similar way by letting letters or words stand for parts of a sentence and then composing the letters to stand for the way of composing the part of the sentence. So S's and P's in modern grammar stand for subjects and predicates. In ancient Greece, this wasn't so easy because ancient Greeks did not know algebra. They couldn't use letters for numbers because actually their numerals were letters. So they had a mental block against using letters to stand for arbitrary numbers. They always sort of stood for something like 200 or 243. But in the case of grammar, he did discover that you should use letters to stand for the parts of the sentence. Of course, in those days it was much more. Ever since that time, we have used Greek letters in our algebras, and Aristotle was clearly the first person to use Greek letters for this purpose. So he then defined, in terms of purely grammatical constructions, the grammatical forms of 24 valid forms of reasoning, which the first of which is one which is called Barbara. Each of these syllogisms consists of 3 lines, 3 sentences separated by a line. The 2 sentences above the line are the premises of the argument, and the sentence below the line is the conclusion. So if you wish to reason that all S are P, one way of supporting this judgment by logical reasoning is to establish the premise that all S are M and all M are P, where M stands for what they call the middle term of the syllogism. Then the second of these 24 syllogisms states no M are P, all S are M, and from these you can validly conclude that no S are P. Nowadays we can draw Venn diagrams to illustrate the validity of these judgments. And then he defined a proof as a sequence of sentences in which each sentence is either a premise or it is the last line of one of these 24 syllogisms, and the first 2 lines occur earlier in the proof. That's interesting because it's one of the first uses of induction to define the syntax of a valid proof. And nowadays we use the same form of induction. The induction occurs because the word proof appears twice in that definition, once at the beginning and once at the end. So it violates a basic principle that Aristotle put forward, that the term that you are defining in a definition should not appear in the right-hand side of the definition itself. It seems to be a circular definition, but in fact it works in grammar. It works for all our programming languages. Their grammar is defined by similar circular definitions. It's actually what enables a proof to be as long as it needs to be and no longer. It doesn't have to be infinite. A finite proof, actually I haven't got a clause which gets me out of this recursion. Please help me. A proof is either a single line, which is both a premise and a conclusion, and its conclusion, which is a premise, or a sequence of sentences which satisfy that property. Now, the interesting thing is that we use the same definition to define what is a valid computation of one of our computers. An execution of a program is a very long process, much longer than any arguments that anybody would like to follow, but every line of it follows a certain rule which indicates that the result of executing of an instruction follows from the nature of the instruction and the immediately preceding line. So the definition of execution of our programs uses the same pattern of definition as Aristotle used for defining his logic. Now, the other very interesting thing about Aristotelian logic, which Aristotle realized, is that the validity of a proof is entirely independent of its subject matter. It doesn't matter whether you are reasoning about politics or about crime or about biological species. You can test the validity of the proof by checking every line to see that it satisfies the definition that I've given on this slide. And so he realized that essentially it was a mechanical or computational process to decide whether a proof was valid or not. And today, of course, computers are very good at checking this kind of proof. They're very much more complex proofs. And they're even getting very good at generating proofs. They use the same kind of logical principles of deduction that Aristotle pioneered to assist in mathematical proofs of very deep theorems like the four-color problem and the Kepler conjecture, which have only recently been proved by mathematicians with the essential aid of a computer. The four-color theorem, and both the four-color theorem says that every map can be colored with only four colors and with no two adjacent countries sharing the same color. The Kepler conjecture says that if you pile the oranges on a pile of oranges on a barrow, then the natural way of piling them will lead to the most oranges in a given space. So neither of these conjectures could be proved without the assistance of a computer generating and checking proofs in the same way as Aristotle did. So the realization that proof is independent of the subject matter is, I think, a foreshadowing of the invention of the general purpose computer, whose computations remain valid independent of how the results of those computations are being applied and what real-world phenomena the values inside the computer are actually standing for. Some pretty bright ideas, I think, Aristotle had in this case, and they are still valid today. Let us get them across to our students, and confident that we are teaching basic principles of some durability, nearly 2,500 years in this case. Here's an example from biology. When Aristotle was a young man, he took an interest in biology. He was living, I think, in the island of Lesbos, and he used to get the fishermen every morning to come in with their catch and show him and name him all the fish in their nets. And he saw sharks and mackerel and rays and other fish, and came to the conclusion that sharks and rays were not actually fish, but belonged to a different genus. He called them Salacians. And so he could specify in his biology statements like all sharks are Salacians, all Salacians inhabit the sea, therefore all sharks inhabit the sea. That's an example of Barbara, because all of the lines are annotated as A-type lines. The Barbara has A as its three vowels in. Celarent has EAE, that indicates a syllogism of the form no Salacians are fish, all rays are Salacians, and therefore no rays are fish. Now there are 24 of these, and it was quite difficult to remember them, so these mnemonic names were important. But arguments which followed Aristotle's patterns were taught in all schools or in all universities in Europe for, let's say, several hundred years. I haven't got documentary evidence of that. They were applied to things other than biology, which I think might have been a mistake. They were used in sort of schoolroom disputations on various subjects, philosophy itself, judicial reasoning, and so on. But biology is the kind of subject where clearly this kind of reasoning is suitable in drawing the consequences of the discoveries of biologists. From the classification of biology gives a lot of scientific material on which you can base simple deductive conclusions based on Aristotle's logic. Well, some things about Aristotle's logic have been superseded. Thanks to Frege, a German mathematician of the 19th century, we know that all of the 24 syllogisms can be summarized in a single logical law, which is actually more powerful than all of them put together. So I wouldn't recommend actually teaching Aristotelian logic. So let's move on to Euclid. Euclid, like Aristotle, wrote his writings and his discoveries were taught in schools for many hundreds of years in Western Europe, and even in Britain, they've really only recently gone out of the syllabus. Well, if you're talking about somebody who's over 2,000 years ago, I suppose 20 years is quite recent. I would like to call him the father of the geometry of space, and he was a Greek living in Alexandria around 300 BC, not long after Aristotle. And the story is that he was inspired by the applications of his geometry to the measurement of land. In Egypt, of course, the Nile floods every year and wipes out any boundaries that you might have drawn on the ground. And therefore it was important to survey the ground and re-establish where the boundaries were. And so one would expect that the measurement of land and the surveying of land was an important practice in ancient Egypt. Nowadays, the discoveries of Euclid are still being used in surveying, map making, navigation, astronautics, and in all our computers, in all the graphics of all our computers, on all the screens of all the computers, in displays, in televisions, in animated films, and so on. So I think the principles which were discovered 2,000 years ago and are still being applied ever more widely in daily life are worthy of being taught in our schools, hopefully as part of computer science. Why not? Euclid is accredited with a systematic application of the technique of proof to geometry. But in fact, if you look, at least in the first book of the Elements of Euclid, you find that nearly all his propositions, which is what he called theorems, are not just proofs in the mathematical sense, proofs of some static truth of mathematics. They are in fact what we would call constructions. They tell you how to draw a diagram which has certain properties. You can draw a figure, a line, a point, which satisfies some desired properties, and at the same time that you are doing your construction, you prove that the construction has the properties that you want it to have. This is an idea that that has been put forward and followed by my own research for some time, that we should write programs in the same way, making sure that they satisfy the desired properties as you write the program. And the program is like a construction. It tells you how to get to a result that you want, rather than tells you something about some static thing that already exists in the real world. Now, Euclid's constructions were described in the same way as computer programs, as a set of instructions with assignments, sequencing, subroutines, parameters, preconditions and postconditions, and proofs. So let's have a look at the very beginning of the Elements of Euclid. He begins with 5 postulates, of which I've put 2 on this slide. The first of them is actually expressed in an active sort of way. To draw a straight line between 2 points. And this describes an action of drawing a straight line between 2 points. And it says between any 2 points you can draw a straight line. And he implies that there is only one line that you can draw in that way. The second one I won't need, so I'll move on to the third one, which says to draw a circle with any center and a radius, with any center and radius. And the fifth one is the famous parallel postulate, which is, has always been believed to be slightly more doubtful than the others, and which is now known not to hold in the real universe. He expressed these as the 5 basic actions of his programming language, and he used them to make all the constructions in all of his proofs. Now he added to the 23 definitions, of which the first illustrates the kind of thing that he thought of as a definition. A point is that which has no part. Now, the interesting thing about that is that the right-hand side of this definition is not a mathematical formula. So this is not a mathematical definition. The right-hand side is a description of something that we could recognize in the real world, or perhaps we should say an idealization of something that we can recognize in the real world, namely something that is so small that it has no part. It is a point such as you might draw with a very sharp pencil, only very much sharper. Circle is given a similar definition, and the center of a circle similarly. I think he defines that as the point that is equidistant from all points on the circumference. And definition number 20 says, an equilateral triangle is a triangle and has equal sides. This is a definition in which the right-hand side is a mathematical definition. It's referring to triangles and equal-sidedness, which are concepts that have been introduced earlier. Do we have a little glass of water? No? Perhaps I could send out for one. Thank you. And then he added to these 5 common notions. These are they. 2 things that are both equal to a third thing are equal to each other. If equals are added to equals, the wholes are equal. And similarly for subtracted, things which coincide are equal, and the whole is greater than the part. He recognized that his geometric postulates, 5 of those, were not the whole of logic, and he was going to use some logical principles which were more general purpose than would apply which would apply to other branches of reasoning besides geometry. So he called those common notions because they were common to other branches of reasoning. And then he gets on to the real business, which is the proof of 48 propositions, the first of which is to construct an equilateral triangle with a given side. And the last two express Pythagoras' theorem. Now, the best analogy that I can give is that propositions are subroutines in his programming language. Subroutines that can be called by name or number repeatedly in later proofs to perform useful constructions which are needed in those later proofs, just as we write subroutines to express ideas that are going to be used repeatedly in our more useful programs, our later programs. But the important thing he realized that to use a subroutine safely, you need to prove that it has the properties that you want it to have, and the properties that are going to be used in the proof of in the proof of the calling theorems, which of course is what the way in which we use all theorems of mathematics and logic and computer science today. So I'm going to give you proof number one, proposition number one. Given a line, to construct an equilateral triangle with that line as its given side. Has anybody seen this proof before? Anybody studied Euclidean geometry? Right, I see a number of grey hairs. Oh, well done, yes. Grey hairs and even bald heads here. So let me astound you. I thought I was really blown away by this proof. I suppose I must have had a look at it. Well, there's only one thing we can do. We've got 2 points, and we have one proposition which tells us what we can do with 2 points. We can draw a circle whose center is 1 point and whose radius is the line itself, like that. First step of the construction, draw that circle. Second step of the construction, anybody? Draw the other circle. Oh, thank you so much. Okay. Next step. Yes, you can probably see it. Yes. Choose one of the places where the circle intersects. Which one? Oh, of course, the top one. Any other votes? Do you think the proof won't work if you choose the bottom one? Very important point. Euclid's constructions were non-deterministic. He didn't always say exactly what the value was going to be. There you are. Well, here's what you've suggested. Choose a point. Let's call it C, where the 2 circles intersect each other. So Euclid's language had assignments in them. You could assign a value to a name. There's a rather restricted form of assignment in which you're not allowed to reassign a new value to the same name. That, as you may know, is called a single assignment language, and it's very close to the sort of functional programming language that I know Simon loves so well. Of course, the final step of the construction is to draw lines between, using postulate 1, between the point C and the 2 ends of the given line that you started with. As I say, it's a non-deterministic language in which you could have done the... So it left some freedom to the person who was using this construction to use it in either direction that is desired. the actual surveyor who was drawing the equilateral triangle, because those are the edges of the field that belongs to the lord of this manor and not the squire of that parish, could draw it in either direction. Now, nearly all programs of today are non-deterministic. And one of the things that makes modern programming a little bit more difficult than when I was started in the subject is you cannot predict exactly what your program is going to do. But you still better make sure that whatever it does, it's correct. And Euclid's proofs do exactly that. So, the proof. The proof starts by asserting that the two lines which I have drawn with blue equal signs on it are equal. And the reason for that is because they are both radii of the left circle. And a similar argument shows that the two lines with a red dagger on are also equal. And now he uses one of the common notions. Common notion says any two things which are equal to some third thing, that is the line at the bottom, are equal to each other. So now we have a triangle in which all the sides are equal to each other, which by definition 20 is an equilateral triangle. QED. Lovely old quaderat demonstrandum. Lovely words to write at the end of a beautiful proof. Well, what do we learn from this? That Euclid was the designer of the world's first programming language. It had primitives, which he called postulates. These are the primitive actions available in the programming language, like draw a circle with a center. Definition of new names, choose a point C on, sequencing of commands, draw this construction and then draw that construction, subroutines, which he called propositions, we nowadays call them theorems, draw an equilateral triangle, preconditions, that is parameters about which something can be stated that is allowed to be assumed by the writer of a subroutine. So given a line that is straight, that says you can apply this to any line whatsoever, and then the postconditions are the conclusions of the proof that the triangle is equilateral, and every time you call this subroutine, you can assert as a postcondition that after the subroutine is completed, the triangle drawn, the triangle delivered as a result, is indeed an equilateral triangle. Now, of course, I'm very interested in Euclid because I have made the ideal of writing programs together with their proofs as my research goal, indeed throughout my research life. So for 40 years or so, I have been pursuing an ideal without realizing that Euclid had already achieved it. So you see begin to see the advantage of teaching principles and ideas, conveying understanding that has stood the test of time. And 2,000 years is not too short a time to apply this principle to. Well, I think I have time to move on to another one of my idealist philosophers. I think if one considers people in the past who you would like to think of as computer scientists, you could choose quite a number of philosophers and logicians. I think Aristotle was a computer scientist before computers were invented, on the basis of his logic and indeed his analytical approach to science in general, which he applied to physics, meteorology, and many other branches of science. He had a sort of analytical approach, which I think is one that we want to cultivate in computer scientists. Euclid, obviously, but not, I think, Plato. Plato was much more a humane subject. He took a view of philosophy that would appeal more to real life, to politics, to justice, and to philosophy. Another of the philosophers of the past, whom I would like to nominate as my prize for the, shall we say, for the 14th century AD, would be William of Ockham. No, sorry, yes, the 14th century. He was a medieval monk who studied and taught at my old college in Oxford, Merton College, for a while. And he wrote quite a number of works, Summa Logicae and De Praedestinatione et Futuris Contingentibus. The second one of these is the one that I will be talking about. The objective of studying logic in those days was its application not to biology and not to the measurement of land, but to the most important subject for a monk in Oxford in the 14th century, which was theology. And the purpose of logic was to analyze the paradoxes which people could put forward to prove something false about the world and about God. The argument that William of Ockham and his contemporaries and predecessors in the Middle Ages was that God knew from the beginning what the future holds for man, and therefore man can have no free will. That's an argument that you can say, except we use the word science instead of God. Since science predicts everything that is going to happen, or at least if we knew everything that existed now, Newtonian science, the Newtonian view of science, is we could predict everything that was going to happen. And therefore we have no free will. This argument is also not true. So how did they... we can draw an analogy with programming. The programmer who wrote a program knows exactly what that program is going to do. Or he would do if he, like God, was infinitely clever. Therefore, the implementation of the programming language has no free will. It's got to do exactly what the program says. But as I said earlier, a program can be non-deterministic. A program does not have to dictate precisely what is going to happen in every nanosecond of its execution. And that is the solution discovered by William of Ockham, actually probably discovered by St. Thomas Aquinas or even earlier than that, but it's the one that he put forward that God, who programmed the whole world, left in it a certain amount of non-determinism, and it was man who could select which of two alternative paths the real world was going to take. And so I'm using an analogy in which the implementer or user of a program has a choice when there is a non-deterministic branch, which way that branch is going to go. And that leads to an idea about future time, which is nowadays called branching time, and is the basis of reasoning about the behavior of programs, which caters for non-determinism. The story that is used to illustrate the solution to the paradox is the story of Jonah and the city of Nineveh. This is the authorized version of the Bible. God told Jonah to tell the citizens of Nineveh that their city was going to be destroyed in 40 days' time. So the people of Nineveh believed God and proclaimed a fast and put on a sackcloth from the greatest of them even to the least of them. And the story ends that God saw these works and that they had turned from their evil way, and he repented of the evil that he said he would do unto them, and he did it not. So what actually happened in the branching time is that although it was predicted that the citizens of Nineveh would continue along a downward path which led inevitably to the destruction of their city, just in time they managed to make an alternative choice which led them upwards in this tree, and the city of Nineveh was spared. And so the paradox is resolved. God could not be accused of having made a prophecy that in fact was not satisfied, because all of God's prophecies are conditional on an expectation of what man might in the future decide. And if man decides to mend his and her ways, then when the prediction doesn't come true, it doesn't actually invalidate the prophecy. The prophecy has actually had the required effect of causing the mankind to change their ways. Now, am I right? It's 15. Yes, thank you. I think I have wrapped up. I have told you.